So today we are going to talk about the signed numbers, which is section 2.6 in our book. Okay, so before going to dive into the details of the signed numbers and solving the relevant questions, we have to see that what is meant by the signed numbers. Okay, so in previous sections we have seen that the unsigned numbers, okay, if we had the unsigned decimal numbers, so those can be represented with the n number of bits, where n can have any number. So suppose if we have n equal to 3, so it will contain 2 raised power 3 means 8 numbers in binary. Okay, so 3 bits can represent 8 numbers in maximum in the binary numbers, which will be from 0 to 7. Okay, so you can see that all the numbers here are positive, which will range from 0 0 0 0 0 1 0 1 0, okay, and 0 1 1. Similarly, 1 0 0 1 0 1 1 1 0, okay, and 1 1 1. So each number here is basically, this one is the 0 and this one is 7. So these are starting from 0 and ending up to 7. So the question rises here is that what if I want to represent the negative numbers with the same number of bits? What would happen here? So in order to do so, what has happened in the signed numbers is that the leftmost bit or the MSB has been assigned to the signed numbers. Okay, so this is the signed number, this is again the signed number bit. Okay, so what are these basically? So these are the bits used for sign. Okay, so what does it mean by sign? So if these are 0, so 0 means positive, and if it is 1, it means negative. Okay, so in order to do so, what has happened here? So these bits are used for sign. So therefore now if I want to represent different numbers by using these signed values, so here this will be 0. So all the numbers here with this 0 bit at the MSB would be the positive numbers, while all the ones here will basically denote the negative numbers. Okay, so here what would happen that if we have the n number of bits, okay, so previously for the unsigned numbers, those started from 0 and ranged from 2 raised power n minus 1 numbers. So this was the range. So if n was 3, so the range was basically this one. If this was for n equal to 3, if n was equal to 2, okay, if n was equal to 2, what it was? So it was 0 to what? That was 0 to 3. If n was 4, that was from 0 to 15, and so on. Similarly, now for the signed numbers, what would happen? So the question here is that what would happen? So now the numbers will range from minus 2 raised power n minus 1 up to n minus 1 up to n minus 1. This minus 1. So the range here will be this one. So this was the range for the number of bits in the signed numbers or the total number of binary numbers. So now if n equal to 2, so according to this formula, what would be the range? So the range here would be 2 raised power n minus 1 is this one, okay, up to 2 minus 1 up to 1. So it would be from minus 2 1 up to, okay, so it would be from minus 2 to how much? That would be from -2 to 1, which will also include 0 as well. Okay, so those would be -2, -1, 0, and then 1 for the n equal to 2. Similarly, if we have the number of bits, if the number of bits here are 3, so these will range from -2, 3 minus 1 to 2, 3 minus 1 minus 1. Okay, so how much would it be? It would be -2 up to this one, so it would be -4, and here it would be 3. So the numbers here would be, here the numbers will be how much? Those would be -4, -3, -2, -1, 0, and also 1, 2, 3. So these are 1, 2, 3, 4, 5, 6, 7, 8, total 8 numbers, while here we also have these 4 negative numbers and also 4 positive numbers as well. Okay, so this formula is also a very important formula which shows you the number of binary numbers with the signed integers. Okay, so with this method we can represent any number by using the signed binary numbers, and let us solve some more examples related to this formula, which will be helpful for converting any unsigned numbers to the signed numbers. So stay tuned. Hello guys, so this is section 2.5, which is related to the complements of the binary numbers. So the first question here is this question number 21, in which we have to determine the ones complement of all the parts which are given here. Okay, so what is basically the ones complement? So ones complement, let me have this number here, that is 100, and in order to find the ones complement of it, what we have to do, we just have to take the complement of each and every term here, and by taking the complements here, what will happen? All these zeros will be converted to the ones. This 0 will be converted to 1. Okay, similarly this 0 again will also be converted to what? This will also be converted to 1, while this is 1, and this 1 will be converted to 0, because the complement of 0 is what? Its complement is 1, while the complement of 1 is 0. Okay, so therefore the ones complement of 100 is 011. Okay, similarly, in order to find the ones complement of 111, what it would be? So it would be 0, 0, 0, because it will be the complement of each and every term here. Okay, similarly in part C it is 1 double 1 0, so it would be 00 and 11, because each of the binary number here will be complemented and will be inversed, and if it is 0 it will be converted to 1, and if it is 1 it will be converted to 0, and vice versa. Similarly, let me solve this part E of my question, and it is now 1 00 10 10. Okay, so what will happen? 100 will be converted to the D011. Okay, this 10 will be 01, and this 10 will be 01 as well. Okay, so that is about the ones complement, which is also one of the very important concept in the complements of binary numbers. Similarly, another very important concept here is the 2's complement. Okay, so let us have the question 22, in which we have to determine the 2's complement of each binary number here. Okay, so again the same binary numbers are given here, and in order to find the 2's complement, what we have to do? In order to find the 2's complement of any number, first we have to find the ones complement. Okay, just like here we have this part A. So we have, if a number we have is 1 1, so its 1's complement will be 0 0, and in part 2 of it, what we have to do, we have to add 1 with its 1's complement. Okay, so now here we have the 0 0, so in part B of my question, what we have to do, I have to add this 1 with it. Okay, so what I will get, I will get 0 and this will be 1. So what is this? This is basically the 2's complement. So this is also a very easy and very important method which we can use to convert or complement any binary number to its 2's complement. What are the benefits of 1's complement, 2's complement? We will discuss them in our upcoming videos when we will solve the relevant questions. Okay. Similarly, if we have a number here that is 110, okay, so its 2 complement, first of all we have to find the 1's complement. So 1's complement it has will be 0 0 1. Okay, this is what, this is 1's complement. Okay, and to find the 2's complement I have to add 1 with it. Okay, so what will happen, this is 1 1, so it will become 0 1, so it will be 1, and this is 0. So what is this? This is now the 2's complement. Okay. Similarly, our part C here is 1 0 1 0. Okay, so again the 1's complement of it is 0 1 0 1. Okay, that is the 1's complement, and in order to find the 2's complement I have to add with it this 1. Okay, so how much would it be? 1 1 is, this is 0 1 1 1 0. Okay, so that is what, that is the 2's complement. Okay, similarly now let us take another example here and let me solve it. So let me take the problem F here, that is 1 1 0 0 1, that is F 1 1 0 0 1. So in order to find the 2's complement of it, what we have to do, first of all find the 1's complement, so that would be 0 0 1 1 and 0. Okay, that is the 1's complement, and that, let me write it here as well, 1's complement. Okay, and in order to find the 2's complement, let me add this 1 with it, so it will become 1 1 1 0 0. So that is now what, that is the 2's complement. So that's it for today, in which we have discussed the fundamentals of 2's complement, 1's complement, and solved the exercise questions of our book by deploying that concept. So I think it's enough for today. You are encouraged to solve the other questions which I did not solve here, and these are left for your own practice. So if you have any question, you can ask me in the comment section. Take care of yourself, and I will see you soon. Welcome back, guys. So this is question number 23 of section 2.6 related to the sign numbers, and here we have to express each decimal number in binary as an 8-bit sign magnitude number. Okay, so the first number here is this 29, that is the plus 29. So what we have to do, as this is positive, so as we have previously shown you that the MSB bit, which will be the 8-bit here, will be 0 in case it is positive, and if it was negative, okay, the bit the MS bit here, or the leftmost bit, was basically 1. Okay, so what we have to do, first of all, let me convert this one to the binary number, or the 8-bit binary number here. So here we have 2 0 1 2 3 4 5 6 and 7. Okay, so the conversion from decimal to binary is already covered in this series, and I will put the link of that video in the description box. So the first thing here will be this 16. Okay, 16 plus 8 will be 24. Okay, and 24 plus 4 will be 28. 28 plus 1 will be 29. Okay, so all the others will be 0. Okay, so now this one is the binary equivalent of 29. Okay, let me now separate it out. So this will be how much this is now, plus 29. So as the bit here is 0, so it shows that it is a positive number, so therefore it will remain like this. So that is the binary equivalent of this plus 29. Similarly, the second number here is 85. So B 85, and that is the negative number. So first of all, let me find the binary equivalent of 85. So in order to do so, what I will have, this 2 to the power 4 is 16, 16, 32, 32 is 64. So 64 here will, this will be now 1. Okay, 64, and how much is left now? 85 minus 64. So 85 minus 64 is now 1, and 21. 21 is left. So what I can get here, this one is now 1, this is 0. So here I will have 64, and this one is 2 raised to the power 4 is 16. Okay, so this would be 80. Okay, so 80 here. So now 5 is left, so therefore 2 to 4, this is 4, and here this one is 1. Okay, so this one is also 0. So now this one is what? This one is equivalent to the plus 85. Okay, now in order to represent the negative 85, what we have to do, we have to make this bit as 1. Okay, but all the other bits will remain same. So here it will be 1 0 1 0 1. Okay, that is the binary number, and it is now minus 85 in the 8-bit sign magnitude number. So that is the solution of part B of my question. Okay, this is the equivalent, or is 1 2 3 4 5 6 7 8 bit equivalent of this minus 85. So what is the step here? First of all, we have to find the magnitude of the positive number, and then we have to change the MSB of the binary number according to the sign of my decimal number. So that is the part B of my question. Similarly, in order to solve the part C here, that is how much? That is 100. So again, I have to use the 6th bit here. So the 6th bit here will give me 64. So 64, and this is 32. So 64 and 32 is how much? That is 96. Okay, so how much is left now? Now we have 4 left. Okay, so we have to make this bit as 1, while the others will remain 0. Okay, so that is 0 1 2 3 4 5 6 and 7. Okay, so this is now what? This is for plus 100. Okay, so as the number here is already plus 100, so that is the binary equivalent of this plus, because now you can see that this bit is 0. So 0 means positive number, so that is for the plus 100. Okay, so now let me solve this minus 123. In order to represent the minus 123, what we have to do, let me solve it here. So part D of my question, or let me go down, minus 123. Okay, so in order to represent it with the binary numbers, so here I will have 0 1 2 3 4 5 6 7. Okay, these are all the powers of 2. So now in order to do it, 2 raised to the power 7 is how much? That is 128. So that is higher than 123, so I am not going to use it. Similarly, now I have to use this one. This is 64. 64 and then 32, that is 96. 96 and 16. 96 plus 16 is how much? That is 11. So that would be 112. Okay, so how much is left now? 123 minus 112 is 110. So 11 is left. So therefore I will also include 8. So after including 8, 3 is left. So therefore I will make these two 1 So this is 2 raised power 1 is 2. That is 2 raised power 0 is 1. So this will be how much? That is my number, which is plus 123. Okay, so now in order to make it negative, what we have to do? We have to make this sign for this number, this also represents positive sign, while in order to make it minus 123, what I have to do? I just have to make this bit as 1 while the other will remain same. Okay, so that is okay, 1 2 3 4 5. Okay, so this one and last two are these one. Okay, so that is now the binary equivalent of what? Minus 123. Okay, so that is for today, in which we have discussed the method of converting or expressing any signed decimal number with the help of a 8-bit sign magnitude number. So I hope it is now understandable, and I will see you with some more relevant examples in our upcoming videos. Thank you so much, and if you have any questions, please ask me in the comment box. Welcome back. So this is question number 24 of section 2.6, and we were talking about the sign numbers. Okay, so in today's lecture we will talk about the expression of each decimal number as an 8-bit in the ones complement form. Okay, so as I have previously told you that ones complement is one of the very feasible form for the negative decimal numbers. Okay, so the first term here we have is this minus 34. Okay, and we aim to represent it by using the ones complement. So first of all, what we have to do in first step we have to represent it in the binary form. Okay, so to represent it in the binary form, again using the same procedure, so 20, 21, 22, 23, 4, 5, 6 and 7. Okay, so again I'm using the same sum of the product method of decimal to binary conversion, because I feel this is one of the very easiest one, and one can very easily remember this as well. Okay, so in first step of this procedure, what I have to do, I have to convert this minus 34 and take plus 34 of it and convert it into the binary one. Okay, so plus 34, so here I can see that this 2 raised power 5 is the 32, which is the very nearest lower possible number of this 34. So writing it this one. Okay, so after it 32 and 34, there is only the difference of 2, so I can see that this 2 raised power 1 is the 2. Okay, so these all are now zeros, making all these others are zeros, and I can see that this is what? This is the binary representation of this plus 34. Okay, so this is the binary representation of plus 34. In order to represent the minus 34 in the ones complement form, or taking the negative of it, what I have to do, I have to take the ones complement of it, and that would be the second step. So in second step, I have to take the ones complement of it. So taking the ones complement of all the binary digits here, what I will get here, I will get here 1 1 0 1 1 1 0 and 1. Okay, so that is the binary number which represents minus 34 in the form of its ones complement. Okay, so that is the answer of minus 34 or part A. Similarly, in order to represent this plus 57 in the binary number, so we can very easily see that this is a positive number, and it can be very easily represented by using the simple decimal to binary conversion, and there is no need to represent it in the ones complement form. So therefore we will just write it in the binary form. Okay, so plus 57, writing it in the binary form will give me how much? So using the same formulation which we have used here, so this 32 is the nearest lower form, while this 2's power 6 is 64, which is greater than 57. So I will take this 2's power 5. Okay, after it, this is what? This is 2's power 4, 16. 16 plus 32 is 48. Again writing it. Okay, so 48 plus 8 is how much? That is 56. Okay, and this one is 57. So writing these terms as zeros. Okay, so the binary representation of it is 0 0 1 1 1 0 0 1. Okay, so that is the binary representation of plus 57, and as this decimal number is in the positive signed form, so therefore I am not converting it to the ones complement. Okay, the third one here, part C, is minus 99. Okay, C is minus 99, and that is the decimal. So again, using the same convention, in which in first step what I have to do, I have to take this plus 99 and convert it to the binary form. Okay, so converting it to the binary form, again going back here. Okay, so here this 2 to the power 6 is how much? This is 64. So writing it here as well. Okay, because 64 is the nearest possible lower number than 99, while here this is 2 to the power 5 is 32. 32 plus 64 is how much? This is 96. So I'm also writing it. Okay, so 96 and 3 is left. So this one is 98 and this is 99. All other terms will remain 0 here. Okay, so that is what? That is the binary equivalent of my number, which is 0 1 1 0 0 0 1. Okay, so that is the binary number. Now in the second step, what I have to do, I have to take the ones complement of it, and this ones complement will be 1 0 0 1 1 0 0. Okay, so that is the form which represent the negative of this plus 99, so it will be minus 99. Okay, so this is what? This is the minus 99, and also shows me that this is the value which corresponds with this minus 99 as well. Okay, so that is the ones complement of my number which I have represented here. So here the last one is this plus 115, and again we can see that this is a positive number, and to represent it, what we have to do, we have to write the binary equivalent of it. Okay, so while writing the binary equivalent of it, what we will do here, this is the 64 plus 32 is 96. Okay, 96 plus 16 is how much? 96 plus 16 is 112. Okay, so how much is left? 3 is left, so this is now 3. This is basically the binary representation, and there is no need to take the ones complement of it. So therefore this will be 0 1 1 0 0 1 1. That is the binary equivalent of this plus 15. So that is the end of my question, in which I have represented the negative numbers with the ones complement, and similarly the positive numbers are represented by the corresponding binary numbers. So thank you so much, and I will see you with some more questions in our upcoming video. Welcome back, guys. So this is question 25, and here I have to represent each of the decimal number as an 8-bit in the 2's complement form. So the steps will remain same as we have done with the ones complement, so that wherever I will have here the negative numbers, I will first take the positive number, convert it to the binary one, and will take the 2's complement of it, and that would be the corresponding negative number of that decimal number. So the first question, or the first thing here I have, is this 12. Okay, so we can very clearly see that this is a positive number, so just writing the binary equivalent of it will be the sufficient one. So again taking these terms here, so 0, 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6 and 2, 7. Okay, so the binary equivalent of this 12 will be how much? So here I can see that 8 is the closest possible number which is less than this 12, while this is 12 power 4 is the 16 which is higher than this. Okay, so 8 plus 4 is 12 while taking the others as 0. Okay. So this is basically the binary number which corresponds with it, and there is no need to take the 2's complement because this is already positive number. So 1 1 0 0, this is the answer of it. Similarly, in part B of my question, this is minus 68. Okay, so here I have to represent it, and therefore I have to take 2 steps. So in first step, what I have to do, I have to take the binary equivalent of plus 68. So the binary equivalent of plus 68 would be taking it here. So this is now 2 to the power 6 is 64. This is here. So 64 and the 68, the difference between them is 4. So therefore there, this is the 4 while taking others as zeros. Okay, so what is this? This is the binary equivalent of it. So 0 1 triple 0 1 double 0. Okay, in second step I have to find the 2's complement of it. Okay, so in order to find the 2's complement of it, what I have to do, I have to take the 1's complement of it. So 1's complement of it will be 1 0 triple 1. Okay, and 0 double 1, this is the 1's complement, and in order to take the 2's complement of it, I have to add 1 with it. So adding 1 with it, what I will get, 1 1 is 0, 1 will be carried here, this is 0, this 1 here, so 1 1 1 1 0 1. Okay, so what is this? This is the 2's complement, which is the alternative of this minus 68 in the binary number. So that is the binary equivalent of minus 68 in the 2's complement form. Okay, so that is the number. Similarly, the third one here is 101. Again, this is a positive number, and just taking the binary equivalent of it will be the sufficient one here. Okay, so I'm not going to convert it here, but you can try it over it, that just writing the binary equivalent of it will be the sufficient one. While the last one here is minus 125. Okay, so D is minus 125. Okay, so that is again a negative number. So again I will follow 2 steps. So again, first step, binary equivalent of plus 125, how much would it be? Let me write it here, converting it by using it. So what I will get here, it will be, this is 64, 32, 96. 96 plus 16 is 112. 112, 8 is 120. This is 124. Okay, so 124 and 1 is 125. So that is what? That is the binary equivalent of plus 125. So here it will be 0 1 1 1 1 1 and 0 1 1 2 3 4 5 6. Okay, so that is the binary equivalent of 125, and in the second step I have to find the 2's complement. So in order to find the 2's complement of it, first of all I have to take the 1's complement. So 1 0 0 0 0 0 and 1 0. Okay, 1 2 3 4 5 6 7 8. Okay, this is the 1's complement, and adding with it 1. Okay, so it will be 1 1 0 0 0 0 0 1. Okay, so what is this? This is the 2's complement, which is the binary equivalent of minus 125. Okay, so in this manner we have covered that how to calculate the 2's complement of the negative numbers while the positive numbers binary equivalent will remain same. So that's the end of today's lecture, in which we have solved question 25, and I will see you with some more interesting questions in our upcoming video. See you soon. Welcome back, guys. So this is question number 26, in which we are given different binary numbers, and these are the signed binary numbers, and we have to determine the decimal equivalent of these numbers. Okay, so as previously discussed, these are basically the 8-bit numbers. Okay, so let me have these 8-bit numbers. Okay, so these are all the 8-bit numbers, while here this 8-bit is the signed bit. Okay, so whatever here will be, if this will be 0, so what is meant by 0, this is a positive number, while if it is 1, this it means that that is a negative number. So here now let us first use these bits here and see that what are those numbers by converting it to the decimal equivalent. So the first number here is, this is part A, and that is 1 double 0 double 1, okay, double 0 and 1. So these are basically the 2 raised power 0, 2, 1, 2, 2, 2 raised power 3, 2 raised power 4, 2 raised power 5, and 2 raised power 6, while this is a sign bit. So this sign basically represents that this is a negative number. Okay, so this is for the sign, while others will be used for the decimal conversion. So here that's why it will be 1 multiplied by 2 raised power 0. Similarly, it will be 0. Here it will be 0 as well, while this one will be multiplied with 2 raised power 3. Okay, this one will be multiplied with 2 raised power 4. Okay, now these zeros are also multiplied with these terms, but the resultant of this multiplication will be 0. That's why I have written them here like this. Okay, similarly 0 multiplied with 2 raised power 5 is 0, and this one will also give me 0. Okay, now adding them, what will I get? This is 1 plus 0 plus 0 plus 8 plus 16 plus 0 plus 0. Okay, so how much would it be? That is 16 plus 8 is 24 plus 1 is 25 with this one. So this is now how much? That is 25, while this one is 1. So therefore this equivalent will be minus 25 in decimal numbers. Okay, so the equivalent of it is minus 25. Similarly, now converting it into the decimal as well. So now we can see that this bit here is 0. Okay, so that's why it would be a positive number. Similarly, 0, 1, 2, 3, 4, 5, 6. Okay, this 6 is how much? This is 64 plus 32, 96. 96 plus 12 is 96 plus 12 is how much? 96 plus 12 is 8. That is 108. Okay, 108 plus 4 is how much? That is 112. So this is now plus 112, or the decimal equivalent of 0 1 1 1 0 1 0 0. So that is in decimal, so that is in binary. So now the decimal equivalent of it is this plus 112 in this one. Okay, now solving the last of it, which is now C of it is 1 0 and all others are 1. Okay, so how much would it be? So we can very easily see that this is now 1, so it basically shows me the negative number. Okay, now as this one is the negative one, so all the others except this one are here 1 1. So here it will be 1 1 1 1 1 1. So how much would it be? So that is 2 raised power 5. So that is how much? That is, so here I will have multiplying all these terms. What I will get? Here I will get 1 plus 2 plus 4 plus 8, okay, plus 16 plus 32, okay, and that would be in 9's. So 32 plus 16 plus 8 plus 4 plus 2 plus 1. So this is 3 plus 4 is 7. 7, 8 is how much? 7, 8 is 15. 15 plus 16 is 31. And this is minus 63. So the decimal equivalent of this number is how much? That is minus 63 in decimal. So that is the procedure in which the sole method or the crucial task is to find that whether the number is negative or positive, and all of that basically depends upon these two MSBs, the most significant bits, either that can be 0 or 1 as well. So that's it for today, in which we have discussed the signed number conversion from binary to the decimal number. So thank you so much. This is question number 27. And here we are asked to determine the decimal value of each signed binary numbers in the 1's complement form. Okay, so all the numbers here which are mentioned, so these are basically the 1's complement representation of any decimal number. So in previous lectures we have determined the binary equivalent of the positive and negative numbers. So today we are going to discuss the binary to decimal number conversion. Okay, so basically there are two methods. The first method here is, let me take the first part of it here. So 1 0 0 1 1 0 0 1. Okay, so that is basically the 8-bit binary number. Okay, so what we have to do here are basically two methods. Let me first discuss the first method. Okay, so according to this method, what we have to do, let me write it by using this green color. So what we have to do, this is the 1's complement. So the number we have here is 1 0 0 1 1 0 0 1. Okay, so as the leftmost bit here is 1, so we can see that this is a negative number in the decimal equivalent. Okay, so what we have to do, first of all, we have to take the 1's complement of it. Okay, so 1's complement of it will be 0 1 1 0 0 1 and 0. Okay, so that is the 1's complement of it, and then we have to convert it to the binary one. So again the binary equivalent of it will be how much? So again writing 2 0 2 1 2 2 2 3 2 4 2 5 2 6 and 2 7. Now writing these numbers here, what we will get, this is 0 1 1 0 0 1 and 0. Okay, so multiplying each term with the corresponding bit here, what I will get here, I will get here 2 1 is 2, this is 2. Okay, this 1 multiplied by 4 is 4, this will be 0, this will be 0. This is how much? 2 raised to power 5 is 32. Okay, and this is what? This is 64. So now getting it, what I will get, 64 plus 32 is how much? 96. 96 plus 4 is 100, and then 102. So that is 102, and previously we have seen that it would be a negative number due to this bit, so therefore it will be minus 102. So this is the method number 1, in which we have seen that the answer is minus 102. Similarly, in order to find the decimal equivalent of it by using the second method, so second method here will be, here the second method will be, so let me first write here 2 0 2 1 2 2 2 3 2 4 2 5 2 6 and minus 2 7. We have to write the negative sign with this 2 raised to power 7, and now we have to write the bits here. So let me use the blue color for the method number 2. So now writing the bits here, so I will get here 1 0 0 1 1, okay, 0 0 and 1. Now converting it, what I will get, again the same procedure. So here I will get 1, okay, plus this is 8, this is 8, this is 16, okay, and this is how much? This is 128, so negative of it is minus 128. Okay, so now I will have 128 plus 16 plus 8 is how much? That is 24, plus 1 is 25. So here I have 25. So here minus 128 plus 125 is how much? That is minus 103. Okay, so at the end we will get, when 103 we have to add 1 with it, so I will get here minus 102. Okay, so this is from the method number 2, while this minus 102 is from method number 1. So we can see that both the answers are correct. So you can see that whatever method you want to use, it will be up to your convenience. So whichever method you like to do here. Okay, so that is the first video in which we have discussed the two methods which you can use. So this is method number 2, which I have represented with this blue color, and this is method number 1, which is done by this green color. Okay, so I will see you with these two parts in our upcoming video. Till then, take care of yourself. Welcome back, guys. So this is question 27, and this is part B of 8, in which we have seen that there are basically two methods to convert any signed 1's complement form to the decimal one. Okay, so previously we have talked about the part A of it. So now let us start part B of it. So for it, let me first remove it. Okay, as I have told you that whatever method you found convenient, you can do it. So let me use method number 2 for solving the part B of my question. So here again, in order to solve it by using the method number 2, so what I will get, there will be 2 0, 2 1, 2 2, 2 3, 2 4, 2 5, 2 6, and minus 2 7. Okay, now writing the bits here, what I will get, I will get here 0 1 1 1, okay, 0 1 and double 0. Okay, now converting it and multiplying each bit with the corresponding value here, what I will get here, 0 0, here what I will get, here it will be 4, okay, plus here this will be 8 is multiplied by 0, this is 16, okay, plus 32, and this is 64. Okay, so converting them to the decimal equivalent, what I will get, 64 plus 32 is 96, 96 plus 4 is 100, and this is 116. So this is 116. This bit is already nullified by multiplying this term with the 0, and we have got this 116, which is already a positive number. So therefore the answer will remain same, which is 116. Okay, similarly, in order to solve it by using the method number 1, and this was a method number 2. So in order to solve this question by using the method number 1, we can see that here the number is 0 1 1, okay, 0 1 0 0, and here we can see that this bit is already 0. So therefore we will see that we can conclude from it that the answer of it will be positive. So therefore we are not going to take the 1's complement of it, and the number here will remain the same here. So therefore converting this one, okay, when I will convert it to the decimal one, what will happen? It will be the same procedure which we have followed here. So therefore the answer of it will also remain 116 in the decimal form. Okay, so we have seen that the answer from both methods will remain same here. Okay, similarly, talking about the last part of our question, so let me talk about the last part of our question. So the last part of our question is this one. Okay, and let us solve it by using the method number 2 again. So method 2, following the method 2 here. So the question here is 1 0 and all the 1's here. So therefore what I'm going to do here, I am going to follow the method number 1. So here, by following the method number 1, what will happen, it will be a lengthier method. Why? Because all the bits here are basically 1 here. Okay, so you have to use your own common sense that which method you should have to follow. So therefore when I will follow method number 2, this will be a lengthier one, and you have to make many calculations, because you can see that this is 2 0, 2 1, 2 2, 2 3, 2 4, 2 5, 2 6 and minus 2 7. Okay, so writing bits here, what I will get 1 0 and all others will be 1. Okay, so it will be a quite lengthier method, because each bit and each number here will be added together, but not this one. All the others will be added together, and this will be a lengthier process. Despite it, the method number 2, using the method number 2 here, what we have to do here, we have the number which is 1 0, 1 1, 1 1 and 1 1. Okay, so 1 2 3 4 5 6 7 8. So here we can see that this bit is 1, so therefore the answer will be a negative number. Therefore what we have to do, I'm going to revert all the bits here. So here the 1's complement of it will be 0 1, and all the other terms will be 0. So 1 2 3 4 5 6 7, and this one is 8. So all the bits are inverted. So now converting it to the decimal form, what I will get, 2 0, 2 1, 2 3, 2 4, 2 5, 2 6 and 2 7. Okay, writing these bits here, what I will get, 0 1, 0 0, 0 0 0. Okay, so I will get here only this term will be multiplied with it, and I will get 2 raised power 6, which is 64. Okay, so as I have previously told you that the answer here will be negative, so therefore the answer here is minus 64. So from this method we have calculated all the terms very easily. Unless and until we had to find all the terms here, what we had to do, we have to add this one with this one with this one. Okay, all the terms here will be added together, and what we will get here, 3 plus 4 is 7, 7 plus 8 is 15. Okay, 15 plus 16 plus 32, and here it will be how much, that would be minus 128. Okay, so 32 plus 16, this is how much, 48. So 48 plus 15 is how much, this will be 63. So minus 128 plus 63. Okay, sorry, this is 63. So how much would I get? I will get here minus 65. Okay, so as this is a negative number, I have to add 1 with it. So here I will get minus 64. So you have seen that this one, method number 1 here, let me use the red color here. So method number 2 here is lengthier than the method number 2. Okay, so you have to look at your own convenience and follow the method which you find feasible for you to use in any condition. Okay, so that is the end of our question number 27, in which we have gone through different scenarios that whichever method we will use and will be better one. Sorry, this is the method number 1 and this is the method number 2. Okay, so that's it for today, and I will see you with some more interesting questions in our upcoming video. See you soon. Welcome back guys. Question number 28, and here we have to determine the decimal value of each signed binary number in the 2's complement form. Okay, so here the method will remain the same. The only method we will follow here will be that in which I have to write the powers of 2's, 2 1, 2 2, 2 3, 2 4, 2 5, 2 6 and minus 2 7. Okay, so the method here will remain the same as we have to follow for finding the decimal equivalent from the 1's complement forms in our previous videos. But what will be the difference between the 2's complement and 1's complement decimal values? There, whenever we got any negative numbers, we had to add 1 with it at the end, but here we are not going to do so. So therefore the first question here is 1 00 11 001. Okay, so let me write here. So 1 00 11, okay, 001. So these will be multiplied together, and here I will get what I will get here. I will get here 1 plus this is 8. Okay, this is how much? This is 16. Okay, and this is minus 128. So now minus 128 plus 16 plus 8 is how much? That is 24, plus 1 is 25. Okay, so at the end I will get minus 103. Okay, so that is the decimal equivalent of this number, and the answer of it is minus 103 in the decimal form. Okay, similarly for the next question we have, let me remove it, and just by writing their values here, what I will get? 0 triple 1. So here 0 triple 1 0 1 double 0. Okay, so what I will get here? This will be 4 plus this is 16 plus here 32 plus 64. Okay, so adding them together, what I will get? 64 plus 32 is 96, plus 4 is 100, and 16 is 116 in decimal. So the answer of it is 116 in the decimal form. Okay, so that is the decimal equivalent of 116. Now similarly, finding the decimal equivalent of this number, what we have to do, again let me remove it, and writing all the values here, 1 0, all the ones. Okay, and now finding them, what I will get here? This is 1 plus 2 plus 4 plus 8 plus 16 plus 32. Okay, and this is minus 128. So let me solve them. Minus 128 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, this is 63. Okay, 63 minus 128 is minus 65. Okay, so that is the decimal equivalent of it, and we will see that it is now this one. Okay, so that is the sole difference between the 1's complement and 2's complement, what we have seen in our previous videos. And by following the same procedure, which was basically the 1's complement form in our previous video. So what if you use the conventional method, what you have to do? Okay, so in that video, let me use the same procedure here for this number. So if I have 1 0 1 1 1 1 1 1, okay, so this is basically a number, and here this 1 means this will be a negative number. Okay, so if it will be a negative number, let me first invert all these numbers. So what I will get? 0 1, and all the others will be 0. Okay, so once I will get it, let me add 1 with it, and I will get here what? This will be 1 0. Okay, as this is a 2 form, that is 0 0 0 0 1 0. Okay, so I will get this number. Now writing the binary equivalent of it, what I will get? This is the only bit here, and this one here. So this will be 1 plus this is what? This is a 6 bit. So 2 raised to power 6 is 64. So 64 plus 1 is how much? That is 65, and as I have told you that it will be negative number 1, so it is now minus 65 in decimal, which is the same as this one here. Okay, so the same procedure will lie also here, but what you had to do after inverting all the bits, what you had to do, you had to add 1 with it. Same will lie for this one as well. Just take a look at it and give it a try, and you will get the same answer as we have done here. Okay, so that's it for today, in which we have discussed the two methods for finding the decimal value from the 2's complement form. Okay, so that's it for today, and I will see you with some more questions in our upcoming video. See you soon.